We know that when we differentiate, we find out the gradient of a curve, the rate of change of the curve. Now if we differentiate a second time, we get d2y by dx squared, and this is the rate of change of the gradient, or rather the curvature of the curve. And if the second derivative is positive, then that means that the curve is permanently becoming a more positive gradient. So it might have started off as a negative gradient, gone through 0, and then become a positive gradient. If the second derivative is negative, that means it started with a positive gradient, but it gradually turned into a negative gradient. Now these two shapes are known as convex and concave. Easiest way to remember the concave is because it looks like a cave. So I've got a little bear living in my cave. So a cave is concave and the other one is convex. So this is a way of testing if we've got a maximum or a minimum, because if we know that the gradient is 0 somewhere and the curve is convex, then we must have a minimum point. So if the gradient is 0 and the curvature is positive at a particular point, then we know we must have a minimum. If, on the other hand, the gradient is 0 and the curvature is negative, then we must have a maximum. So we can see with some of these examples here that for this quadratic, it's concave just by looking at the shape of the curve, or if we differentiate, we get 5 minus 2x, and if we differentiate a second time, we get a constant value of -2. So it's less than 0 all the way through the curve, so it's concave for the entire curve. And it's got one point which is a maximum, where the first derivative equals 0. So if 5 subtract 2x equals 0, then x equals 2.5. That's our maximum point, 5/2. If we look at the exponential curve, if we differentiate once, it's the exponential, nothing happens. And if we differentiate a second time, nothing happens. And we can see from the graph that this is always positive. It's always above the x-axis. So it's convex for all values of r. The gradient is forever and ever increasing, which is why exponential functions are so important in growth or studying growth. For things like cubics, we have different conditions in different parts of the curve. So if we differentiate once, we get 3x squared, subtract 12x, subtract 9. And if we differentiate a second time, we get 6x subtract 12. Now that is positive when x is greater than or equal to 2, and it's negative when x is less than or equal to 2. So 2 is this important turning point or change. Everything before it is concave. As we can see, we've got a cave shape. And everything after it is convex. And we can find a maximum or a minimum, because if we take our first derivative, set it equal to 0, 3x squared subtract 12x subtract 9 equals 0. So x squared subtract 4x subtract 3 equals 0. So x subtract 2 all squared subtract 7 equals 0. So x equals 2 plus or minus the square root of 7. That gives us our max and min point. So our max will be at x equals 2 subtract root 7, and our min will be at x equals 2 plus root 7. And the point in between is 2. That's where we change from being concave to being convex, and that's called a point of inflection. And that's where the second derivative equals 0. We get a change between concave and convex. Obviously it could be the other way around. So let's look at some potential questions. So find where it's concave. So to be concave, we know that the second derivative must be negative. So let's differentiate once and differentiate again. And we need to know when is this negative, and that's for all values of x less than or equal to 0. We want to show that we've got convex this time, so that means the second derivative needs to be positive. So there's our original function. If we differentiate once, we get 2e to the 2x plus 2x. And if we differentiate a second time, we get 4e to the 2x plus 2. Now, e to the 2x is positive for all values of x. And so 4e to the 2x plus 2, not only positive, it's greater than 2 for all x, and therefore is convex for all values of x. So this point of inflection is where it changes between concave and convex, and we can find that it's when the second derivative equals 0. So to show we've got concave on one interval and convex on another interval, so we're interested in the second derivative, so let's work that out first. So the first derivative is 3x squared subtract 4x subtract 4, and the second derivative is 6x subtract 4. So on negative 2 to 0, the second derivative, if we put in negative 2, we get negative 12, subtract 4, negative 16. And if we put in 0, we get negative 4. So the second derivative is between negative 16 and negative 4. So yes, it is negative. It's less than 0 for all those values, and therefore is concave. Whereas if we look at the interval 1 to 3, substituting 1 we get 2, substituting 3 we get 14. So it's positive all the way through there, and therefore it's convex for all of that. Now obviously at some point it's swapped between being convex and concave, and we can find out where that is exactly. It's when this second derivative equals 0. So 6x subtract 4 equals 0. So when x equals 2/3, and therefore when y equals, substitute in 2/3, subtract 2 lots of 2/3 squared, subtract 4 lots of 2/3, plus 5. Y is 1.74074, or as a decimal, so as a fraction, at 47/27.